Hello everyone, let's move on to our next topic in lecture number 10 in the lecture series of application of thermodynamics. The topic is the solvent extraction. So as we are continuing our topic Nernst distribution law, so as a part of that it is time for solvent extraction. So what is the principle of solvent extraction? The principle of solvent extraction is completely dependent on the Nernst distribution law. What is the law? Now the partition coefficient is the ratio of the concentration of the solute in two different solutions where the two different solvents are immiscible with each other, and this ratio is a fixed ratio, is the temperature is kept constant. So under this principle, under this law, the principle of solvent extraction is actually will be discussed. So suppose we have to extract an organic substance. Suppose iodine is dissolved in water, okay, and we have to extract that iodine from water with the help of another liquid which is immiscible with water. Say it is chloroform, it may be carbon tetrachloride, it may be ether or anything else which is immiscible with water. So what is the volume? The volume of the solution. Which solution? Aqueous solution. So the volume of the aqueous solution is V milliliter or V cc centimeter cube, and that of chloroform, that is the extracting solvent, is LCC. Okay, listen to carefully, okay, all the things. Now the amount which is dissolved in the main solution, that is in water, that is iodine. I will take always the reference of iodine, water, chloroform. Actually iodine is the solute, water is the main solution, and chloroform is the extracting solvent. Okay, so if I use the names water, chloroform, then you must take into consideration that the general terms are used, such as the solute, the main solution, and the extracting solvent. Okay, so the amount of dissolved substance in the main solution is x0 gram. That means x0 gram of iodine is now dissolved in VCC of aqueous solution. And if you shake this VCC solution with LCC of the extracting solvent, that is chloroform, then some iodine will go into chloroform and some will still remain present in water. Okay, and that amount is x1 gram. So the unextracted substance in the solution after extraction is x1 gram. Okay, so what is the amount of extraction? The extracted amount should be the difference of these two. That means the amount which was present before extraction minus the amount which is present after extraction. So x0 minus x1 gram of the solute is extracted by LCC of solvent. Now what is the ratio? Actually, before taking the ratio, let us find out the concentration. Okay, so the concentration of the solution in the extracting solvent, the solvent has extracted how much amount of solute? Now x0 minus x1 gram of the solute. And what is the volume of the solvent? It is L. So the amount of solute divided by the volume of the solvent. Now it is not solvent, it has also become a solution. So that chloroform solution or the extracting solution of the extracting solvent is LCC now. Okay, so the ratio is the concentration. So x0 minus x1 over L is the concentration of the solute within the extracting solvent. And what about the main solution, that is the aqueous solution? The amount which is left after extraction, is x1 gram. What is the overall volume of the main solution? It is V cc. So x1 by V gram per cc is the concentration of the solute within the main solution. So their ratio should be what? The ratio is actually, according to the Nernst distribution law, is Kd, that is the distribution coefficient or partition coefficient. and this is a constant definitely. So concentration of the substance in the extracting solvent and concentration of the substance in the main solution. So their ratio is x0 minus x1 by L over x1 by V. Okay, and L is here in the numerator and in the denominator, and V has gone to the numerator. So multiplied with the terms with x0 and x1. So it has become x0V minus x1V over x1 into L. Okay, now let us rearrange. So this is equal to Kd, and let us rearrange this equation. So after having rearranged this equation, we get x1 L Kd equal to x0V minus x1V. Okay, and what is the expression of x1? It is actually x0 into V over L Kd plus V. So we are getting the term x1, that is the unextracted solvent after first operation. The amount which is still left, which is left behind in the main solution, is x1 gram, and you can express this in terms of x0. So x1 is the unextracted amount of solute within the solvent after first operation, and x0 is the amount of the solute before the first operation. So if you undergo via the same operation repeatedly, that means you take another LCC of the extracting solvent, and the solution which is obtained after first operation, if you shake that solution with L amount of the extracting solvent, then the unextracted amount of the solute which is left in the aqueous solution should be what? It should be x2, and it can be expressed in terms of x1. As here x0 and x1 are related, for after the second operation x2 and x1 should be related by same manner. Okay, so amount of the unextracted substance in the solution after extraction, that means after first extraction, then what should be after second extraction? x2 should be x1 into this parameter V by LKD plus V. Let us see. Now if a second extraction is run with LCC of extracting solvent, that means you took LCC of the solvent at the time of first operation. Now you are taking again LCC of the solvent during the second operation. Okay, so in that case the amount of the unextracted substance, which is x2, that must be expressed in terms of x1, likewise the previous equation. So this x2 must be equal to x1 into V by LKD plus V. Okay, and you have the expression of x1 here with the help of the previous equation. In the previous equation, x1 was actually x0 into this parameter. So x0 into this parameter is written here instead of x1, and here this V by LKD plus V is written here as it was already present. Okay, as the second term of the right hand side. So putting the value of x1, this is written instead of x1, and this is already present. But these two terms are same and they are getting multiplied with each other, so it will become the second power of this parameter. So it will be actually x0 into V by LKD plus V's whole square. So after second operation, x2, here in the power you can see the term 2, isn't it? So after the third operation, x3 must be reflected in the power. It should be whole thrice. It should be power, there should be the power whole cube, isn't it? After nth operation, there should be n in the power. Okay, and all other terms would remain the same. Similarly, after nth extraction, as I have said, the quantity left behind would be xn with expression what? Just all the things are same except this power. Instead of this 2, you are writing here n, because here instead of 2 you are writing n. So nth operation and nth power. So this way you are getting equation number 1. So what is the overall amount of the solvent you are using here? You are performing n number of operations with LCC of solvent. So n into L should be what? It should be the overall amount of the solvent. Now if this overall amount of the extracting solvent is used in a one lot, then what would happen? Then you are performing a single operation, isn't it? And for that single operation, with instead of L amount of extracting solvent, you are now using NLCC of solvent. So here in this place, in place of L, you should write NL. And since you are performing only one single operation, so here should be, instead of N, there should be 1. Okay. And let us say the unextracted solute, in that case, if it is written as X, then what should be the expression of X? The expression of X should be, all the things are same. Instead, 2 in 2 places we are making the change. Here the power, instead of N we are writing 1 here, and instead of L we are writing here NL. Okay, so thus you get equation 2. So how this equation number 2 is coming here, let us discuss. Now if the entire quantity of the extracting solvent would be used in one lot, that is NLCC, then the amount of unextracted substance would be this one. Okay, so this is equation number 2. Now which amount is greater? This amount or this amount? Xn is greater or X is greater? It's very simple. Here it is V and it is V plus something, that is the numerator is greater than the denominator is greater than the numerator. Okay, so it is some fraction which is less than 1. Okay, so if you take power of any fraction, it would increase in just according to its power, in that order it would increase. Suppose you are taking square of 0.1, then it will become 0.01. If you take cube of 0.1, then it will become 0.001. So the minimum value of n is 2, isn't it? So definitely, since it is a fraction which is bearing the value less than 1, so definitely this value must be much more lesser than this value, because here in the power there is only 1. So this whatever be the value of the denominator, maybe V is added with some large value. Instead of LKD, you are adding NLKD, but still whatever be the larger value of the denominator, the second power multiplication, you cannot overcome that. So definitely this value is greater than this value. Okay, that means X is greater than Xn. That is, Xn is less than X. So the unextracted solute in the main solution is less here if you perform the operation in portions, at least in 2 number of operations instead of 1. And if you increase the number of operations, just divide the solvent in 4 parts, then n would be 4. Divide the solvent in 10 parts, then n would be 10, and the unextracted amount would be much lesser than the operation you perform by using the overall solvent in one lot. Is it clear? So this is the principle of solvent extraction. Okay, therefore what type of conclusion we can draw here? That with increasing number of operations, that is greater value of n, the amount of unextracted substance Xn will be much more smaller. Hence it is more economical to use the solvent in portions. So this is the principle of solvent extraction. What is the principle? Now it is more economical to use the solvent in portions. Okay, so that's all from this topic, and thank you. Have a nice day.